Welcome back everyone. In this lecture we will see abstractly how to construct representations of finite groups. So, for that we need to recall what is presentation of a group. So, let us begin. So, let us say we are interested in constructing representations. So, now by definition representation is just a group homomorphism from G to GLV. So, let us fix one representation and work with that. So, now if we know actually some generators of G, then we will be able to say immediately that this rho is indeed determined by its action on the generators. So, what I making? So, here is the remark. So, it is already given that this is a group homomorphism. So, that means it is a representation. Suppose let us say S is generating set for capital G. So, S is subset of G and then S generates. So, that means, so there are let us say k number of generators for the G. So, now it is easy to see. So, easy to see that rho is completely determined by its action on capital S. So, what is the meaning of that? So, I will leave it as exercise. Suppose if we know the set rho of G I for all this 1 to k, I 1 to k. So, then we know rho. So, basically if we have rho and xi, let us say two group homomorphism from G to GLV and then rho of Gi equal to xi of Gi for all I range from 1 to k, if this is given. So, then we can immediately say that rho equal to xi. So, this is given the fact that rho and xi are to begin with a group homomorphism and they agree on the generating set, then we can immediately say that rho is same as xi. So, that means rho is completely determined by its action on S. But then like how do we actually construct such rho just using the action on its on the generators of the group. So, basically we are asking that is it enough to give only rho of G I? So, the answer is no, because there are relations that will actually be there between these generators and we need to be careful with those relations. So, we need to basically check and take care of those relations. So, what I mean by that? Okay. So, maybe like what we are interested in. So, if we think about it, so rho is merely a map from G to GLV. Okay. So, you just take even though it is a group homomorphism, it is first of all a map. So, that means, so I can choose some Mi from this GLV and then I can actually just send this Gi to Mi. Okay. So, if we start with some map like this, can I actually get, so given this map, so given this set map, do we have, does there exist a group homomorphism rho from G to GLV such that rho of Gi equal to Mi. So, the answer to this question, not always. So, it is not always you can expect a group homomorphism such that this rho of G equal to Mi for all given set maps from S to GLV. So, then how do we get this or make sure that such group homomorphism exist? So, if we actually start with the, let us say, row which is a set map from S to GLV, and then sending this, let us say, GI to MI, and then we are interested in extending this map to the group capital G. But then what one can actually say immediately, that from this set map one can immediately get an extension to the free group generated by capital S. Let us call it f of s to be the free group generated by S, free group generated by S. So, then it is immediate that using the universal property of the free group, that you have an extension row from f of s to this GLV, where row of GI is given by MI. So, the same map that we had here, that can be extended to a group homomorphism here. So, this is guaranteed, and this is just a set map. So, now we are interested in actually getting a group homomorphism from G to this GLV, but we know that since S is the set of generators for the group G, then we always have actually a surjective map from f of s to this capital G. Okay. So, of course, there is some kernel. So, that kernel actually kind of gives us that, let us call this surjective map pi. The kernel of this pi, this is going to be a normal subgroup inside your f of s. Then using the first isomorphism theorem implies that this f of s modulo the kernel is going to give us isomorphism between this quotient and the group G. But we can make sure that this kernel is indeed generated by some set of elements, and they are called relations among the generators of this S inside G. So, let us say the kernel pi is generated by some R. So, where R is some set of elements. So, let us call them some R1 etcetera, some Rm. So, now what it is? So, basically in this case, when G is isomorphic to f of s modulo, let us call it, this is n of r, where n of r is the normal subgroup generated by this relations R. So, this is the normal subgroup generated by R. Then in this case, we call this S to be the set of generators of G. So, S will be called generators of G, and this R will be called the relations of G. So, of course, we will be able to come up with various different set of generators and as well as various different set of relations. So, these relations are supposed to be in terms of the generators that we have chosen. So, they are like some equations that you get it from the group G. Okay. So, let me just rewrite, for example, like this R I is going to be, so which is the capital R, which is the set R1 etcetera Rm. So, this R I is going to be functions in G1 etcetera Gk. So, it will be just a word that actually you actually get it from these G1 etcetera Gk, because this is going to be an element inside your f of s. So, it is going to be given in terms of G1 etcetera Gk and their inverses. So, that is why I am denoting this Ri by Ri of this G1 etcetera Gk. So, this is how you can actually write down G in terms of the generators and relation, and so instead of writing in this form, so most of the time in the books we actually use this G as with the angle bracket S and then a slash with R. So, these are called generators and these are actually relations. Okay, so now if we go back to our original question, so we started with rho, which is a map from S to GL of V, and we are interested in actually getting a map from G to GL of V. So, from this we immediately realize that this rho can be extended to a map from F of S to GL of V. Now, since this capital G is quotient of this f of s with the kernel n of r, then we want this map rho to factor through from G to GL of V. So, we are actually interested in looking at or getting this map, another map which we are going to call it again rho. So, that rho is induced from this rho that we have it from f of s to GL of V. So, how do we make sure that such map actually exists? So, to ensure that this rho factors to pi, so we can actually see that this G is given by f of s modulo the kernel pi. So, as long as the kernel pi, which is the normal subgroup generated by the relations, if that is indeed contained inside the kernel of this rho, if this is contained in the kernel of rho, so then in that case we will be able to say that the above map indeed factors through. So, let me just again write it. So, you have f of s and then you have GLV here, and then it just factors through here. You have f of s modulo n of r, and this is your group G. So, that means we are interested in actually getting. So, we know that f of s and this is our rho. So, the kernel rho. So, this is going to be isomorphic to image rho, which is a subgroup inside GLV. So, now we want to have a map from G to GLV. So, for that, so all we need to actually ensure that this n of r that is indeed contained in. So, n of r is indeed contained in kernel of rho. So, what does it mean in terms of the generators? So, we have chosen rho of G I to be M I, and we have certain relations in terms of this R I. So, these relations are actually there inside our group G. So, this is holding, these relations are there for I range from 1 to m inside our group G. So, the assignment that we have made, G I goes to M I. If these M I matrices satisfies this relation, then in that case we will be able to say that this normal subgroup generated by R contained in kernel of rho. Okay. So, all we need, so this condition n of R is contained in kernel of rho is equivalent to saying that when I take this relation R I and then substitute this M 1 etcetera M k, so then we should get the relations inside your G. So, that means R I is should be inside kernel rho. So, that is what we want to have for all I range from 1 to m. So, that means we want for all I range from 1 to m this relation that is there R I of G 1 etcetera G k equal to E should be satisfied by the generators, sorry, by the images M 1 etcetera M k. So, in that case we will be able to say that the map that we had from rho to f of s to this GL of V, that indeed factors through from G to GL of V. Okay, so this is a abstract way of getting a representation of the group in terms of the generators and relations, and most of the time this actually works, at least theoretically this is actually very useful way of constructing representation. But for all practical purposes we will actually use the actual realization of the groups and then how it is acting on the spaces and sets and so on. For example, we used a symmetric group acting on this standard basis. Similar to that, like other groups like diagonal groups and so on, they come up with natural actions on some sets, and we use those actions in order to actually get the representations. But this is again a very important way of getting representations. So, what is the upshot? So, upshot is, so the group is, let us say, given by generators S and relations R. So, let us say the generators are given by G1 etc. Gk, and the relations are again given by R1 etc. some Rm. So, now in order to construct actually a representation of G, so then what we do, we just pick some matrices MIs from GL of V. So, for I range from 1 to k. So, we want to actually send row of GI to MI. So, that is the idea, and they are not randomly chosen. So, they must satisfy the condition that the relations, when I take Ri and then substitute this M1 etc. Mk, so that should be identity on V, and this should be true for all 1 to M. So, if we are able to pick invertible matrices Mi satisfying the relations that we have it in the group, then we will be able to make sure that we have a group homomorphism from G to GLV sending Gi to Mi, and that defines as representation. So, let us look at one example. So, let us look at this S3, and it is easy to prove that S3 is generated by one transposition 1 2, and then this another it is actually correspond to rotation 1 2 3, because I am realizing S3 as a diagonal group D3. So, if we take these generators 1 2 and 1 2 3, this is the 3 cycle. So, this, let us call this 1 2 as S and then 1 2 3 as R. So, then it is not very hard to prove that this S3 is generated by S and R with the relation that R cube is identity, and then S square is identity, and S R S is R inverse, and one can easily check this. So, this is the presentation of S3 with these generators. So, like I said before, we should be very careful. The generators, for example, can change, and as well as according to that the relations also can change. For example, let us just look at the same group S3. So, one will be able to say that for example, like 1 2 and 2 3. So, this also can generate S3. Maybe let us call it, this is S1 and then this is S2. Then with these generators the relations will be S1 square and S2 square should be identity, and then S1 S2 S1 should be same as S2 S1 S2. So, so one can check, we can have different presentations for the same group with respect to different generators. So that is expected, but it is always, if you are interested in coming up with a nice representation, then it is our duty to actually pick up a nice presentation of the group. So that is how one will be able to construct a meaningful representation. So let us stick with the first presentation. So where S3 is generated by S and R with S square 1 and R cube 1 and S is R inverse, this presentation. Now we can immediately get a two dimensional representation defined as follows. So we want to define this two dimensional representation. So we can simply send the transposition to this matrix -1, 0 and 1, and then similarly the 3 cycle to this matrix -1, 1 comma 0, and one can immediately check that this defines representation. So for example, to check it defines representation, we need to just check these relations. So let us check only one relation. For example, we can check S square is just 1. So to check that, we need to just check that -1, 0 1 square of this matrix is exactly the identity matrix. So let us compute this. So if we compute, -1 times -1 is +1 and then 0, and if we take this and this this is 0, and similarly if we take this and this, it's 1 minus 1, which is 0, and this is 1 again. So it's we get the identity matrix. So I will leave it to you to check other relations. So by just declaring what will be the images for the generators, we will be able to say this is indeed a representation. And whenever we write this defines representation, it is assumed that we have checked the relations. Indeed, the representation that we have defined, that is irreducible representation. So maybe let me just check that. So recall that in order to prove two dimensional representation is irreducible, it is enough to prove that it has no common eigen vector for the action of S3. So let us recall the representation rho of this 1 2 is nothing but -1, 0 1, and then rho of 1 2 3, the 3 cycle image is nothing but -1, 1 0. So now we want to claim that this representation, two dimensional representation C2, where the action of S3 is given by this, is indeed irreducible. So in order to prove this, we prove that it has no common eigen vector. So if there is an eigenvector for the entire action of S3, then that means these two matrices also must have common eigenvector. So we are going to prove that these two matrices have no common eigenvector. So this A and B have no common eigenvector. So in order to check this, first we will compute eigenvectors of this capital A. So you can immediately see that this matrix being upper triangular, the eigenvalues of this is just +1 and -1. So the eigenvalues of capital A is +1 and -1. Now if you look at the eigenvalue, sorry, eigenspace for the eigenspace for this eigenvalue -1, you can immediately see that this is going to be eigenvector -1, 1 comma 0. So, this is spanned by this vector 1 comma 0. So, now since we are dealing with only 2 dimensional space, so if the minus 1 eigenspace is 1 dimensional, then definitely the eigenspace corresponding to 1 also must be 1 dimensional. So, this V1A, the eigenspace corresponding to the eigenvalue 1 for the matrix A, that is supposed to be 1 dimensional, but if you do the computation, so this is going to be exactly spanned by this minus 1 2, and we can directly do the computation and then see this minus 1 0 1, and then if we compute minus 1 2, so then we get exactly this is minus 1 and then this is going to be 2. So, that means so these are the eigenspaces, and then C2 is indeed decomposed as V minus 1A direct sum V1A. So, we have computed what will be the eigenvectors for the action of this capital A. So, now to check A and B have no common eigenvector, it is enough to check that these eigenvectors are not going to be eigenvectors for the matrix B. So, recall that B is nothing but minus 1 1 0. Now, we need to check this E1 which is 1 0, and then this another eigenvector x, let us call it x minus 1 2. These are not eigenvectors for B. So, let us do the computation. If you do the computation, B E1 is going to be exactly this column vector minus 1 1. So, definitely E1 is not eigenvector, and similarly Bx, if you do the computation, again you get minus 1 1, and so that implies that this is also not eigenvector. So, both x and E1 are not eigenvectors for B. So, that proves that A and B have no common eigenvector. That means the representation that we define it is indeed irreducible representation. So, like I said, it is actually a very powerful way of defining representation using generators and relations. Sometime we can get lucky and then we are getting irreducible representations. So, let me actually just list some of the groups, known groups with the presentations. Maybe I will leave it to you to check. So, these generators and relations that are there for these groups. For example, the most important simple group is simple means simplest group is Z modulo NZ, cyclic group of order n, and this is indeed generated by only one element A with the relation that A n being identity. So, sometime I write 1 or identity E to denote group element identity, that is understood. So, now if we take the diagonal group more generally, so then this is generated by one reflection one rotation and one reflection S, and rotation order of the rotation is n, and then of course, the order of the reflection is 2, it is an involution, and we also have this following relation between this rotation and reflection. SRS must be equal to R inverse, but R inverse is nothing but R power n minus 1. So, this can be rewritten as R power n minus 1. So, this is the diagonal group, which is the symmetric group on n gon. Okay, this is the diagonal group. So, I am going to write down presentations for certain groups which will be our running examples to understand the representation theory. We will definitely look at the representations of the cyclic group, diagonal group, symmetric group and so on. For the symmetric group, like I said, we have what is called this coxeter presentation. So, it is generated by this S1 etc. Sn minus 1, where Si is nothing but this transposition given by I plus 1, and with the relations there are actually certain relations. So, first relation, this Si square being transposition, it will have order 2, and some commutation relations are there. So, that is given by Si Sj. So, that will commute whenever I and j are far apart. So, that means the modulus of I minus j is greater than 1, and we have what is called bride relations. So, this is what is called involution relation, and this is commutation relation. So, this is involution and this is commutation, and this third one is called bride relation. So, the bride relation says whenever you take Si plus 1, so then the order of that is going to be 3. So, if you rewrite in terms of equation, so Si plus 1 and Si is supposed to be equal to Si plus 1, Si and Si plus 1. So, this is what reads it as SIS plus 1 has order 3. So, these are the some of the groups that we will be interested in. Definitely, we will actually look at into the representation theory of these groups in this course, and most likely I will not be using these presentations, but you can actually take it as exercise to prove this. These are all the presentations for these respective groups, and it is a very important and interesting exercise. And one will be able to use these presentations also to create more representations of these respective groups. Okay, I will stop here. So, we will actually see first of all how the representation theory of this cyclic group actually works out, and then like later slowly we will develop character theory in order to understand representations of general finite groups. Okay, I will stop here. Thanks.